Hello students, welcome back. Let us continue the concept of finding eigenvectors associated with the eigenvalues. In today's lecture, we are going to do one of the important question. Here you can see the given matrix is symmetric. What is the condition for symmetric matrices? Here Aij is equal to Aj for all I comma j. This implies that A12 must be equal to A21, A13 must be equal to A31, A23 must be equal to A32. So in this way, this is for all I comma j, and diagonal elements may be any real number. Okay, now it's clear that the given matrix is a symmetric matrix. If its eigenvalues are distinct, the concept is if eigenvalues of symmetric matrices are distinct, then the eigenvectors associated with this are orthogonal. Means whatever vectors we will get associated with distinct eigenvalues, they are orthogonal to each other. This is the concept that we have to verify from this example. So let us start with the normal procedure. We have to find the trace. We have done in many examples. So here trace is sum of the diagonal elements, which is 3. SMD, you need to calculate SMD. Here I am going to write SMD directly, which is equal to minus 90, and value of the determinant is equal to 216. After finding all these, we need to write the characteristic equation, which is lambda cube minus trace, which is 3 into lambda square plus SMD minus 90 into lambda minus determinant of A equal to 0. So if you simplify this equation, you will get eigenvalues of this matrix. So lambda is equal to minus 3, minus 6 and 12 are eigenvalues of this matrix. All of you see here, eigenvalues are distinct. Given matrix is symmetric and eigenvalues are distinct. Now let us calculate eigenvector. So for lambda equal to minus 3, you can put this value of lambda in the equation. A minus lambda into x is equal to 0. So lambda is negative 3. So a plus 3i into x is equal to 0. Means in short, you need to add 3 in the diagonal element. So the given uh, equation reduces like this: minus 2 plus 3, which is 1, 5, 4, first row. Then 5, 7 plus 3 is 10 and 5. Then 4, 5 minus 2 plus 3 is 1. So these are the three components: x1, x2, x3 and 0, 0, 0. Now no need to apply here a row transformation, or no need to reduce into reduced echelon form. Okay, no need to find the rank and all. Just you need to select any two distinct equations and use Cramer's rule. So x1 divided by if you use the Cramer, which is 25 minus 40, negative x2 divided by uh, these elements, find the determinant of this, which is 5 minus 20, and x3 divided by 10 minus 25 is equal to k. So x1 divided by negative 15 minus x2 divided by negative 15 and x3 divided by negative 15. This is equal to k. Okay, so x1 divided by negative 15, x2 divided by 15 and x3 divided by negative 15 is equal to k. So x1 is equal to negative 15k, x2 is equal to 15k and x3 is equal to negative 15k. So k is any proportionality constant. So here you can take k is suppose negative 1 by 15. So your vector is x1, which is first of all 1, and x2 here opposite sign negative 1, and x3 is equal to positive 1. So the first eigenvector associated with lambda is equal to minus 3 is 1, minus 1 and 0. Now we have to repeat the procedure. Same procedure you need to repeat for lambda is equal to minus 6. So now we are interested in the last part of this. So because you have studied how to find the eigenvectors in the earlier videos, so I'm going to take it directly now. Okay, so first eigenvector is 1, minus 1 and 1. And if you continue the same process, you will get second eigenvector as one second, let me create some space for writing second eigenvector. Okay, the second eigenvector, which is for lambda equal to minus 6 is second eigenvector. By similar procedure is 1, 0 and minus 1. Similarly, for lambda equal to plus 12, x3 is equal to, which is third eigenvector, which is 1, 2 and 1. So these are three eigenvectors associated with distinct eigenvalues of a symmetric matrix. Now, let me see the orthogonality property. You can see here what we have to prove here. X1 and x2 both are orthogonal to each other, means their product is equal to 0. Also, x1 with x3 dash is 0 and x2 with x3 dash is also 0. Dash means transpose here. I'll do one for you. X1, which is always a column vector, which is 1, minus 1 and 1. And x2 is also column vector, but here x2 dash means take the transpose of x2, which is 1, 0 and negative 1. And if you take the product of these two matrices, you will get here 1, then plus 0 and minus 1 is equal to 0. So here the product of x1 and x2 dash is 0. So here if I consider this as x1 and x2 dash, this is equal to 0. This implies that x1 and x2 are orthogonal vectors. Similarly, we can prove that x1 and x3 are also orthogonal and x2 and x3 are also orthogonal to each other. Means their dot product is 0 in short. These are the vectors. Okay. So if their dot product is 0, then we can say that two vectors are orthogonal or perpendicular to each other. So this is the concept that I wanted to tell you in this video. Okay. So thank you.